All right. So by the end of this lesson, you'll be able to describe when resistors are wired in series, know what measurements are equal and what measurements are summative, and calculate the total resistance when resistors are wired in series. What happened to the lab system? You finished it. You finished? Well, part of it. Oh. The part that you needed to finish. All right. So we've got an analogy. But in order for you to understand the analogy, you got to understand what I'm comparing it to. So, water towers. That seems like a really expensive way to store water. Like, why not have swimming pools? Why do we need to elevate a swimming pool size amount of water 5 stories in the air? Sure. Pressure, water pressure. As you swim deeper in a swimming pool, what happens to the pressure? Increases. Pressure is 100% dependent upon depth. Okay? So, as we swim deeper, you get more and more pressure. So, swimming down here in the water, this would be an extraordinary amount of pressure. Okay? Good with that? Now, the other reason why this is extremely beneficial, and there's several ways. One, if the if the electricity went out, you still have water because gravity fed. Second reason, there are certain peak times during the day where we use water as a society, specifically in the evening and in the morning when people are taking showers. In order to facilitate a constant pressure for everybody in those peak seasons or peak times, we need a lot of big pumps to run that. And then when it wasn't the peak time, we could turn those pumps off and they wouldn't be being used. The water tower now eliminates that problem because you just have one pump continually pumping to fill this up during the peak times. It drains down, and then throughout the day it fills back up, and then drains. Then throughout the night it fills back up, and so you're always having this constant pressure, even though there's different demands on the system. That makes sense? Okay, so it's a good idea. So here's why I care about water towers with electricity. The height of a water tower represents voltage of the battery. Okay, it's your voltage gain. Okay, the higher the water tower, the more pressure there is, the more motivation there is to flow. All right with that? And so if we punch a hole in our water tower, water is going to come out. Okay, there's a motivation. But if we put kinks in our water hose, that's going to act like a resistor. Does that make sense? And if we add another kink to our hose, that's going to act like another resistor in series. Okay? And how much water is coming out per second, that's going to be the current. So the total resistance in series, what's happening to the total resistance as we add another resistor in series? Increases. We just add them up. Good with that? You find that to be the case in the lab. You add another resistor in series, everything got dimmer. Okay. Tell your neighbor. Correct answer is correct answer is elephants. Okay. So here's the deal. The current at every spot in a series circuit is equal to every other spot in a series circuit. Factoid, memorize that. Current is the same in a series circuit. Okay? Why? Because there are no junctions. The current in has to equal the current out. We talked about this idea with rivers last week, where the current at one spot is measured in cubic feet per second. Through narrow, shallow parts of the river, the water's moving faster versus wide and deep, moving slower, but the total amount of water going by a certain point every second has to be the same. There is no other place for the current to go. Okay, there are no junctions. So the current at every spot in a series circuit has to be the same. Good with that? Okay, you measured that to be true. Everybody got around like 1.1 amps. No, it was like 0.1 amps in the lab. 0.111, sorry, 0.11, 0.12, somewhere in there. Good with that? Give that one a shot. Thumbs up when you have a guess. Talk to your neighbor. Tell them why you think so.
Actually, no, I don't.
Just talk about the fact that
Oh, then maybe it's.
Okay, what do you say? Got a vote. I got B and C on the table. Okay. As you take a resistor away, that's going to cause the total current. Sorry, that's going to cause the total resistance to do what? Decrease. The voltage of the battery did not change. Therefore, the current is going to increase. But I thought that you said that current is the same at all points in a series circuit. I did. Okay. Here's what I'm talking about. Okay, making these numbers up completely. Let's say there's 2 amps here, therefore there's going to be 2 amps at every spot along this circuit. If I change the circuit, that's going to change the total current. Okay, again, I'm making these up. 3 amps here, there's going to be 3 amps here, 3 amps here, and 3 amps here. They are equal to other parts in that same circuit. But if you change the circuit, that's going to change the current. Good with that? Okay, you see how those, what this means and what it doesn't mean. The circuit, the current is equal at all points in a series circuit. Okay? Wait for it. Thumbs up when you have a guess. Have a conversation. Correct answer is, we got A on the table. A loud A. Anybody else? I got C. Okay. Okay. So you've got to find the total resistance. We need to add up all 3 of those. Okay. So the total resistance is equal to 12 ohms. The total voltage is 24 volts. So the total current is equal to 2 amps. Okay. This C would be correct. B would be correct if you just hooked this straight away to the 24 volt battery. And then B would be correct. It wants the total current. Does that make sense? If we hook this straight away to this, then you'd have 6 amps going through that. Great question. Okay, so folks, here's the deal. Since I know the current, the total current, because it's a series circuit, the current everywhere is equal to 2 amps. There's 2 amps going through all of each of those resistors. Does that make sense? Does that answer your question? No. Sorry. Ask the question again.
Like, if it asks you instead of the 4 resistor spot, like a 5 resistor spot, would you add the totals? Would you just add the 3 and the 5?
Oh, great question. No, you would do all of them. It's not like you only take the ones that hit. You get the whole thing. That's a great question. Okay. Next question. So potential drop, another word for that is voltage drop. Tell your neighbor. Okay, what do you say?
Elephant.
Okay, we got C, we got cats and elephants on the table. Okay, so here's the deal. We're going to employ Ohm's law again. Now, we can employ this. So we know this is 2 amps. We have 4 ohm resistor. We're looking for the potential drop or the voltage drop. So we find this to be equal to 8 volts. Correct answer is cats. Okay. Now, here's the deal. Ohm's law is super powerful. Here's the pitfall. When employing Ohm's law, you need to be consistent with what these are measuring. This is the total voltage, the total current, the total resistance. I employed the Ohm's law here for this one. This is the voltage just across the 4 ohm resistors. This is the current going just through the 4 ohm resistor. This is the resistance of just the 4 ohm resistor. Everything's consistent for either the whole thing or just a piece, a part of the circuit. Here's where kids get mixed up is they mix and match those. Don't do that. Ohm's law, you're going to use it all it's going to be all over the place. You're going to use it all over the place. But the thing you need to do is keep the voltage, current, and the resistance all consistent. What is that looking at the total, or is that looking at a piece of the circuit? Okay. Good there. Tell your neighbor. Correct answer is? Correct answer is B. All right. Looking at Ohm's law, this would be, we know this was 8 volts here, this is 10 volts here, and this was 6 volts here using Ohm's law. How we doing? Making sense? Okay, so I want to show you how Kirchhoff's loop rule is employed here. So Kirchhoff's loop rule says the voltage gain equals the voltage drop. In this circuit, this is a loop, one single loop. Voltage gain was based off the battery. It's a 24 volt gain. Voltage drop, 3 ohm resistor had a 6 volt drop, 5 ohm resistor had a 10 volt drop, and the 4 ohm resistor had a 8 volt drop. Okay. This will always work for any loop in a circuit that you draw. Okay. And an analogy for this, I call it chutes and ladders. So voltage has to do with energy. This is like a extension of conservation of energy. Okay. The battery gives energy to the electrons. The resistors take energy away from the electrons. So you have the battery acts like a ladder. You're increasing your height. You have a 24 volt gain. Okay. Then you go through a wire. Technically, the wire takes a little bit of energy away. You measured that on the labs. It was like 0.02 volts or something like that. Okay. But we're going to pretend that the wires are ideal and they don't take any energy away. Okay. But then we hit the 3 ohm resistor, and that takes 6 volts away. There's a 6 volt drop. So we go through a chute or a slide. Okay. And then they hit a wire, and then they go through a 10 volt drop. So another chute, another ladder. And then they go through the 4 ohm resistor. So that's an 8 volt drop. And then you're back on the ground. You come back around and you go up 24 again. Okay, the voltage gain equals the sum of the voltage drops. Okay, so in a series circuit, you're adding up the voltages. Good with that? Any questions there?
I could have moved my
It's all right. Have a conversation. Hey, what do you say? Got a couple votes for A. Several votes for A. Okay. Correct answer is A. So we know that the total is equal to the sum of the two resistors. So this is staying the same, but as this goes down, the total resistance goes down. So as the total resistance goes down, the voltage stayed the same, therefore the total current goes up. It's a series circuit, so the total current goes up in all spots. The current is this guy. Okay, what stays the same here for this scenario? Which measurement stays the same for this guy? We did not change the resistor. Okay, found that the total current goes up because it's series, so the total goes up, everything goes up, same throughout. Therefore, the voltage does what? Also increases. See how we walk through that one? Okay. Same scenario, but what happens? The voltage drop across R1 now. Have a conversation. Tell them why you think so. What do you say?
Did you say E?
Okay. If you tried to employ Ohm's law, this kept you wanting. What happens to the resistance? Decreased. What happened to the current? Increased. You cannot definitively conclude anything based off of Ohm's law here. Okay? You could have said it stays the same. You could have said decreases. You could.
Make sure Jeff does it. Why would he go in your book, bro? He would, John. Is it because he's black?
You could say increase. You could say decrease. You don't know. That's why I'm always asking, hey, which variable stayed the same? If you know, like if you know one of the variables stays the same, you can definitively conclude something else. But here you're like, ugh. So this falls apart. You can't conclude anything with that. So Kirchhoff's loop rule, here's where that comes into play. Okay, we know the total voltage gain is equal to total voltage drop. I'm going to make some numbers up. Let's say that's a 12 volt gain. And let's say this is a 6 volt drop and a 6 volt drop. Totally making these numbers up. That meant that the resistors were identical at the beginning. Okay. Then we decreased the resistance on that, and that caused the voltage across this to increase. Let's say to 7. Again, making these numbers up. what has to be the voltage drop across this guy? I've got a 12-volt gain. Got 12-volt gain. I used to have 6 volts, 6 volts. But changing that, I now have a 7-volt drop here, meaning this has to be what? Has to be 5 volts. We decreased to 5 volts so that the total voltage still adds up to 12. Remember that? Okay, so the moral of that story is when Ohm's law falls apart, like it doesn't give you a definitive answer, employ either Kirchhoff's loop rule or junction rule. Yep. Thumbs up when you have a guess. Have a conversation. Let me throw out this little thing here. On the discovery experiment we did on Friday, every light bulb had the same resistance. They're identical resistors. They're all from the same Christmas tree light strand. Okay? So this is not, these are not identical light bulbs. They have different resistances. Okay, what do you say? All right, so we know that the current's the same throughout. True? Which one had the greatest voltage drop? This one had the greatest voltage drop. Remember, this had 10, this one had 8, and this had 6. Okay, so this is going to be the brightest, medium, dimmest. Correct answer is A. Right with that? Okay, the shortcut would be to look at this equation. This is combining Ohm's law and the power equation. The reason why I choose this shortcut, this approach, is because the current's the same. Okay, so as the resistance goes up, power dissipated also goes up. Tell your neighbor. All right. Correct answer is C. There are actually, you could do this a couple different ways. You could say the total current was 2 amps, total voltage is 24 volts, therefore 48 watts. You could find the power dissipated by each one of these and then add them all up. You'll find in circuits that often there's a couple different ways to come to the correct answer. Okay, so tell your neighbor what you think. All right, let me just tell you. So we're adding 2 batteries or power supplies in series. That's like having 2 ladders. Okay, so you have a 1.5 volt gain and a 1.5 volt gain. And then you have a 3 volt drop. Does that make sense? Okay, so as you add batteries in series, you add the voltage because you're adding more potential gain, voltage gain to that loop. Correct answer was D. Correct answer is D. Dangerous dinosaurs. Dangerous dinosaurs. Okay. Correct answer is, again, dangerous dinosaurs. This is like having an upside down ladder. You know, like climbing this way, and then you're like climbing that way. It's like.
Yeah, I was thinking like one of the straight ones, so like upside down still.
Okay. So bringing real life into this. When you load up your batteries and anything that requires like double AAA batteries, they usually have, you alternate them, right? Okay. That's because the device, the case that you're putting them in is connected so that they are wired in series. Okay, and if you flipped one of those, it doesn't work because it doesn't provide the required voltage. So this would be 4.5 volts. If you had 4 batteries, that would require 6 volts. That makes sense? So every time it adds a battery, you're increasing the voltage by 1.5 volts. Good with that? Okay. All right. There's that. Okay, looking at parallel circuits. Look at all that. Okay, looking at parallel circuits. Tell your neighbor.
But I'm always wrong when I say that. So.
Yeah, because it's
I like skiing this weekend.
Yeah.
Thought about all your stories.
How'd it go?
It was good.
Did it the first time?
Yeah.
Yeah.
We tried snowboarding first, and that was hard. I could not.
Brutal.
I could not stay up.
Brutal.
Skiing was light.
Yes.
Are you doing this?
Skiing, yes. Snowboarding, not good, but
Can you
can do it. No. Skiing, yes. Snowboarding, sure.
Remember that one jump story when he jumped? Oh wait.
Okay, correct answer is? Okay. What is the same, what measurement is the same in a series circuit? What is the same in a series circuit? Current. What is the same in a voltage, in a parallel circuit? Voltage. Okay. Here's why. Here's one loop. That's why it's called the loop rule. The voltage gain equals the voltage drop. So this is 120 volts across this. Okay? The voltage gain on this loop is equal to the voltage drop on that loop. 120 volt gain, 120 volt drop. If we add another loop, that's totally fine because it's an independent loop. 120 volts. Gain equals 120 volt drop. Okay? So, I could draw the schematic diagram of this like this. One resistor, two resistors, three resistors. I could, oh dear. I could do that. And it'd do the same thing. It'd waste a lot of wire, but it's the same thing. Directly hooked up to the power supply. Independently hooked up. Good with that? Okay, so we talked about our water tower analogy. To add another resistor in series, I would just add another kink to the hose. What could I do? How would I add another resistor in parallel with this water tower analogy? Yep. Pop another hole in the water tower and add a second hose. So if I turn this off, is that going to affect this guy? If I turned it on, is it going to affect this guy? Completely independent. Has the same amount of pressure. Good with that? These two are in parallel with each other. Thumbs up when you have a guess. Talk to your neighbor. Correct answer is? Got some A's? A is correct. Okay, so the voltage is the same as the resistance goes down, the current goes up. Okay, good with that? Thumbs up when you have a guess. Have a conversation. Tell them why you think so. Correct answer is A. What's the same in a parallel circuit? Voltage. Which one has the greatest current? The one that has the least resistance. Okay, so there's more current going through this one than this one, and then finally that one, which is different, folks, than what we concluded about series circuit. In series circuit, we said the one that had the most resistance was the brightest. Parallel is the one with the least resistance. Do not just memorize stuff. Figure it out. That make sense? Okay, we'll cut it short there. You know how to do, you got a worksheet due on Wednesday. You know how to do all the series stuff and some of the parallel stuff.